So with our statistics, as I mentioned today, it's going to be a lot of discussion about various parts of the statistics so that going forward we can actually work with things. So first thing we're talking about today is variability and sampling. And then after this we're going to start talking about population parameters. So data is everywhere. Every kind of place collects data so that they can analyze stuff. Newspapers, science classes, economics, medicine, anywhere where variability can occur, and that's just simply things being different. So variability is simply the probability of outcomes being different. The tools of statistics are designed to explain this variability. So there are, let's see here, 4 main types of variability that we have to take into account when we're dealing with our statistics. So what we're going to do is we're going to read through the different types, and you're going to try to see if you can come up with an example that you're going to write down in your notes for each of the different kinds. So our first one is observational or measurement variability. So that is variability that's introduced due to whether our measuring instruments are not precise enough or differences in how two people read the measurement that creates that kind of variability. So for example, let's say you're doing an experiment where you have to time how long it takes for a ball to drop. Our observational or measurement variability for that one would be purely the reaction time of a person actually taking the time. Because if somebody has a faster reaction time when the ball is released, and then they have that same faster reaction time when it actually hits the ground, their time's going to be different than somebody who, say, just has slower reaction time just because that's the way that they are. So that would be one example of an observational or measurement variability. Anybody think they know another one? So our next one here, natural variability or inter-individual variability. So that's variability that accounts for the fact that the members of populations are simply different. Every person is different, so their results from an experiment are going to be slightly different. So like, for example, 2 people who work out the same amount of time at a gym and yet lose different amounts of weight. They're just 2 different people, so even though they work out the same amount, it's not going to affect them in the same way. Or 2 plants are given the exact same amount of water and sunlight, but yet they still grow at different amounts because they're different plants. So there's natural differences between them. Our third type would be induced variability. So this type of variability is in marked contrast to the natural because it occurs when people assign populations or samples to 2 different groups. So you have actually created the differences in those groups. So for example, if you're trying to test to see if a new drug actually does what you want it to do, you create 2 groups. One group gets the drug, the other one gets what they call a placebo, and you see if it actually does what you want it to do. Or another example, 2 groups are tested on memory. So one group's allowed to sleep for 8 hours, the other group only gets to sleep for 4 hours, and you're trying to test to see if the amount of sleep actually affects their memory stuff. So that's induced variability because you've created the 2 different situations there. And then our last type of variability is your sample variability. So what that says is this type of variability that occurs when we take multiple samples from a population randomly. So when you take that sample, your results of that are going to be different if you happen to get a different sample of people. So like populations of cities, that kind of stuff. You always want to get the most random sample you possibly can from within your population. So down here, remember though, through all of our work in this unit, what we're really trying to explain is the variability within the data sets. So it's within either the population or the sample, and then using this to determine if the variability can be attributed to one of the factors above to exclusion of the others. So basically what that's saying is you're going to get data points here, and you're trying to compare it to the other data points to determine, does this variability play an effect in it, or what you're actually trying to figure out, is that actually significant or not. So let's take a look at the back here. So there are many different types of situations, as I mentioned, in which we collect data. They have important differences, and all of them depend on randomization in one way or another. You always want to be as random as you possibly can. So here we have 3 different ways that we collect data. So on the front we talked about our different kinds of variabilities. These are our 3 ways that we collect data. So we're going to come up with an example of each and explain how randomization is a part of this method. So first one here is surveys. So surveys are collections of data from a population where variability is not induced by treatments, but by the sample itself. So surveys, first off, you're just basically asking a whole bunch of questions of people. You guys have all taken surveys. You've all gotten the pop-ups, I'm sure, on your phone. Take this survey, win a gift card, that kind of stuff. So surveys, you're just basically asking questions of people. But to get the randomized population, you've got to make sure you have a completely random sample. So like, for example, if we have a marketing company wants to see which major soda is preferred in the general population, so they take a random sample of the population. They want a random sample of people, or they may end up with a sample that is not representative of the population. So for example, if their sample all happens to come from people who shop at like a Whole Foods store, do those people generally drink soda? No, because if they're going to spend the extra money to go to a Whole Foods store, generally they're in a more holistic life approach. They want the healthier foods. They're not going to drink soda. So that's not a true representation of the entire population that drinks soda. So they want to make it completely random. No. Next one, observational studies. So observational studies are collections of data from a population where assignment of individuals from the population into treatments groups is not under the control of the person doing the study. You can't control it. You are purely just observing what is going on. So, for example, a health organization might want to explore whether a person's state of residency has a relationship to their income level. So they might sit there and try to look at income levels, like so this section here is lower income versus this section, and then they see what's going on between the two of them. They didn't put them in those groups. Those people already naturally in those groups, and they were just observing what was going on. Another example I gave earlier, because I was talking about Weight Watchers to another teacher this morning, you could do an observational study about Weight Watchers, people who work out while doing the program versus the people who don't work out while doing the program. Which ones lose more weight? What happens? That kind of stuff. So observational studies, all you're doing is purely observing what is going on. You have absolutely no control over the groups. All right, and our last way of collecting data is your experimental studies. This one you do control. So you get people, you put them into 2 different groups or 3 different groups, however many groups you want, and each group gets a different treatment to them. So my example would be if you're trying to figure out which kind of dog food is the best. So you get random dogs to participate in the study, and you put them into 2 groups. So one group of dogs gets the dog food you're testing, the other group gets a different kind, and you see what the effects of it are. So if you're trying to see if it helps joint health or if it helps them with their digestive health, and then you'll be able to, yes. So random sampling is critical for being able to minimize variability due to sampling bias. Random sampling can be done using a variety of different techniques. Simple random sampling can be accomplished by using a random number table. We don't actually have the random number table. We're actually going to use the calculator, which can give you a random number generator, which I think works a little bit better. So, if you don't have your calculator, please go get one. Otherwise, you will need it right now. So here's my calculator. If you go to the math button over there on the left, 3rd down from the top, go over to PRB. And now, it's going to be a little bit different. If your calculator looks like mine, you'll be able to have to do it the way I do. If you've got the newer color screens, you're going to have a little list that I'm going to show you in a second. So you want the rand int, that stands for random integer, no repeats. Okay.
What did we click on to get here?
Math over to PRB. We want random number, no repeat. So now if yours look like mine, you're going to type in 1, because in our little table here where we're trying to generate the numbers from, our lowest number is a 1 that we can pick from, comma, our highest number is a 10. Comma is above the 7. Yeah, so in the new ones you have a little list where you put your lower number, that's where you would put your 1.
So it says random numbers between 1 and 10.
Upper number, you put a 10, and then it's got an N. And so for you guys, if you've got the N in there, that says how many numbers are you picking. We're actually picking 5 numbers, so you want to put a 5 in there. And then you keep hitting enter.
How do you put 5?
Oh my God, Tyler, that's smart.
65.6.
Taking your lottery numbers.
What is lottery numbers range to?
Oh, who's got lucky number 9? I'm gonna pick my lottery numbers.
You're finding the average of your 5 numbers. So, I got 66.2 as my average. 67.2, 65.6 I see over here.
65.4.
So, since we all have different numbers, what kind of a variability did we just do? Did we all have the same sample?
No. Yeah.
So this is an example of sampling variability. Because of the random number generator, we all would have had different numbers, or for the most part, we would have all had different numbers.
Well, we have to answer questions like that.
Potentially.
I like that. Pretty simple, you know.
So when we conduct studies, the complete set of all subjects that share a common characteristic that is being studied is known as the population. A lot of times it is very difficult to be able to get the true full population of your study, so we usually end up using just samples of that. So all populations do have a natural or inter-individual variability. Most of the time the entire population is not measured, but a sample is taken to infer the characteristics of the population. So you assume that the sample you've taken is completely randomized, so therefore whatever details you find to be true about the sample is going to also be true about the full population. So still, all populations in theory have population parameters that describe the population. Those would be things such as the mean, standard deviation, and interquartile range. So we're going to practice going through and finding these things once again to hopefully solidify that in your head. So we got 18 students in Mr. Weiler's advanced calculus class took a quiz with the following results in ascending order. They got from 56 up to a couple of hundred. Use your calculator to determine the mean, median, and the quartiles for this data set. Then construct a simple box and whiskers plot for this data set. So what you want to be doing in your calculators, under the stat, you want to enter those 18 test scores into your list 1. And then we'll be able to find our mean, median, and our quartiles like the problem asks us to do. So I'll give you a minute, go ahead and type those in. So again, remember to find your mean, the median, and the quartiles for this data set. We're going to push stat, go over to calculate, and you want the first one. You want the 1-var stats. Now again, if you have the list, the first one that says list should say L1. The other one should be blank.
And then this is when we hit stat. And then we can go, how do we get that?
Over to calc, and then it's the first one, the 1-var stats. So instead of L1, you should say L2.
So what did you click after that on the
So, over to calc. This first one, X bar, that is your mean. So to the nearest tenth, we got 83.7 is our mean. Your mean, remember you just have to scroll down. Our median is 84.5.
Is that also Q2?
It is also your Q2, yes.
When Q4 be the max, you can do 100.
There is no Q4.
Okay.
Q1 is what?
75.
And our Q3?
93.
93. So go ahead, try to construct your... So remember, with your box plot, you need to have a number line underneath it.
Do you have to put the numbers on the number?
Yes. So let's see here. Our min is 56. Our Q1, 75. Then 84.5. 93, and then our max is 100. So you do want to kind of estimate the numbers that should be a little closer together. You want to have those ones closer together. And then the 3 points in the middle, your Q1, your median, and your Q3 make up your box. Your min and your max get connected to it with just the line. Next part. They want us to find our interquartile range. Your interquartile range is your Q3 minus your Q1. So our Q3 is a 93. Our Q1 is a 75. So what is our interquartile range? 18. Next part of that question. In theory, what percent of the data should lie between the first and third quartiles? 50%. Next part of that question wants to know, is that true for this data set? So if we look up here at our list, we're looking for the numbers that fall between 75 and 93. How many numbers fall between 75 and 93?
You can't count 75 or 93?
Nope. 1, 2, 3, 4, 5, 6, 7,
Yes,
8. 8 out of the 18 scores is roughly, what, 44%?
Well, yeah, but and then the other on the outside is the same as the outside.
But we were looking for the ones that are in between it.
Why is it the
So,
weird
is this true for the data set? No. See, what is the population standard deviation for this data set to the nearest tenth? How do you interpret the standard deviation? Population standard deviation is that funky little circle with a line going across the top. So to the nearest tenth, look in your calculator, go back up if you need to. What is our population standard deviation? 11.7. So how do you interpret the standard deviation? 11.7 means that on average a data point lies 11.7 units away from the mean. On average.
So you got the
Point lies 11.7 points away from the mean. That's if you're looking for sample standard deviation, but we had the full population of his entire class, so we wanted the population standard deviation this time. So then D, what percent of the scores were within 1 standard deviation of the mean, and then within 2 standard deviations of the mean? Round your percents to the nearest percent and show your work. So if we're looking for one standard deviation above or within the mean, you've got to do your mean plus one standard deviation. That takes us one above. And you would have to do your mean minus one standard deviation, because if you are one standard deviation within the mean, you could be above the mean or you could be below the mean. So 83.7 plus 11.7, what do we get? And then 83.7 minus 11.7? 72. So we're going to look through for all of the data points that are between 72 and 95.4. So that's not going to include our 72s. That would start here. That would actually include the 95, because remember, it was 95.4, so 95 is still going to be in between that. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 people out of 18 fall within one standard deviation of the mean. As a percent to the nearest percent, what do we get?
61.
61%. So now we want to do within two standard deviations of the mean. So again, take my mean. We could be up to, so I would do that plus 2 times my standard deviation. Or we could be down to. So let's figure out what those two numbers are. So we would do standard deviations higher or lower. 60.3 would be our lower end. And then what would be our upper end? 107.1. So how many of those scores fell between 60.3 and 107.1? 17 out of the 18. So as a percent,
94.4.
so 94%. Yeah. So sometimes data is grouped in a frequency chart. We still should be able to calculate the basic population parameters with this information that's given in this form. So we have here a company is showing the salaries of all of their 50 employees. So that is everybody that works there. We're dealing with that full population. They want us to first find the mean and the standard deviation for this. So when we go to type this into our calculator, there are two ways that you could do this. You could type 25,000 into L1 5 times, and then you would type 32,000 in 21 different times, and then you would type 45,000 in 14 times. Or you could actually do the frequency list. So if we go to Stat, go to Edit, clear out whatever was in your list 1. So under your list 1, you would put their salaries. 25,000, 32,000, 45,000, 58,000, 75,000, 120,000. I thought that was the intern. So then under your list 2, that's where you would put your frequencies. So 5, 21, 14, 7, 2, and 1. So it looks pretty much just like your table on your paper. L1's got our salaries, L2's got our frequencies. So we are still talking about just one variable though. Even though we have two categories here, we still are just talking about the salary. So there's just one thing we're talking about. So we're still going to do just one var stats. So we want the first one. Now again, if your calculator looks like mine, you have to include your frequency list. So you would hit second and the number 1 to get you your L1, and then comma, second and the number 2 to get you L2. Whenever you have a frequency list, you have to put the L1, comma, L2. Now if you have the little chart there, the first one says list, so you would have L1. Second one says frequency list, you would put your L2 in there, and then you would just keep hitting enter. Second, and then the number 2. And then you hit enter. 42,060. And our population standard deviation?
Are we on this 1 or are we on this 2?
All right, next they want us to find our median. So scroll down, find your median. 32,000. Now I want you to start thinking of, what do we call this number here? That is an outlier. Is anybody else close to making 120,000 other than that one person? No. The average salary is closer down here to this range where our median actually ends up falling, which is the 32,000. So when they ask you why is the median considerably lower than the mean, it's because the outlier makes the mean inaccurate. So what that outlier does is when you actually go to calculate your average, it makes all of those values considerably higher. However, when you're trying to find your middle number, which is your median, that's not going to change. That's still going to be right pretty much where everybody is.
So is the median more realistic than the mean?
When you have an outlier, your median is your more accurate value. So then C, does more or less than 50% of the data set fall within one standard deviation of the mean? Show your analysis. So again, to find if it falls within one standard deviation of the mean, you have to take your mean, add your standard deviation, and subtract your standard deviation to see what values we're looking between. So my mean of 42,060 plus my standard deviation, and then my mean minus the standard deviation, again, to see what range of numbers we're looking at. So our higher end would be 58,627.93. Our lower end would be 25,492. So looking at our table, that would include these values, the 32,000, the 45,000, and the 58,000. So that's 21 plus 14 plus 7 would be 42 people out of 50. What is that as a percent? 84%. So is that more or less than 50%? More than 50%. All right, our last part, although we often have concentrated on experimental studies when data is collected and means are found, many times we use statistics to represent results of surveys where we are interested in the proportion proportion of a population. Proportions are generally expressed as decimals, so that's how you can tell, but sometimes you can get fractions or percents. So a questionnaire went home to all juniors concerning their ability to bring and use mobile devices at school. The questionnaires constituted a census since it went home to all of the juniors. Whenever it encompasses everything, we refer to that as a census. So of these 742 juniors, 564 of them reported having web-enabled mobile devices. What was the population proportion for web-enabled devices? So all you have to do is take the number of them that have it, divide it by the total number of people who answered. So they want us to give the answer as both a decimal and as a percent. So let's go ahead and divide those. What do we get? 0.76 or 76%. And then our last one for today, the proportion of eggs that get cracked in a local egg handling facility is 0.023. If 25,000 dozen eggs are packaged in the factory per day, what should we expect to be the number of eggs cracked per day?
0.023 times 30,000 is 30,000 is 2,500 eggs.
What are you saying?
So you do 0.023 times
25,000 dozen, so if we multiply that by 12, that tells us how many eggs separately are packaged.
690 eggs get cracked daily.
Wow, that's a lot.
25,000 times 12, what do we get? So that 30,000 times the proportion of them that get cracked in a day, or 0.023. Somebody told me 30,000.
Oh, sorry, I thought it was 25,000.
Yep, 2,500. So then we will multiply, what do we get? You should get 690.